De Moivre's theorem says this. He says that if you have z written as r cis theta, meaning you take a complex number and you put it in polar form, right? Then z to the nth, so take this complex number and multiply it by itself over and over and over again, is the same thing as r to the nth cis of n theta. And we worked through a little bit of a proof of that yesterday. Basically taking z times z and getting r cis theta times r cis theta. So we take the r's all come together and we take the thetas and add together. And as we do that n amount of times, we can then condense that relationship to r to the nth cis n theta. Okay? So that is De Moivre's theorem. Now, what I want to do, guys, is I want to go through a procedure here that shows the benefit of this theorem. Okay. Now, I want to go a little bit slower than we did in the last class because we made some mistakes in the last class, and it just got to be kind of a pain in the butt. All right. But the mistakes that we made in the last class, I kind of told them, this is a great example, a great visualization of why De Moivre's theorem is used. Because when we go through this 2 plus 5i, I'm going to raise that to the 12th power here in a moment. And we're going to FOIL it. We messed up FOILing. We just did some multiplication that was wrong at one point, or some addition that was wrong at one point, and then that messed everything else up. Okay? And there are so many different places when I take z equals 2 plus 5i, and I want to find out what that is to the 12th power. There's so much FOILing involved that there's a lot of places you can make mistakes. All right, so I want to go through this and hopefully we don't make a mistake. But I'm going to, we talked about it yesterday. You could write this out as, 2 plus 5i, 2 plus 5i, 2 plus 5i. You could write that out 12 times, right? And I do see people doing this. If I take 2 plus 5i times 2 plus 5i, FOIL these first two here, okay? So when you do that, 2 times 2 is 4. Plus then, we get what, 20i? Okay? And then 5 times 5 is 25. So 25i squared. But that turns into minus 25, right? So then that turns into negative 21 plus 20i, right? Okay. I see a lot of people, guys, realize that, okay, we've now multiplied those two things together, so they're done, right? And then they bring this down and go 2 plus 5i, 2 plus 5i, and they ultimately have 10 more of those things written down, right? And then they grab these two and multiply those two. Does that end up making more work for us than what's necessary? Yeah, doesn't it make more sense to grab those two and multiply those two together? Why? Yeah, because you already know it's negative 21 plus 20i, right? So the idea here, if we can condense this a little bit, is to use this. Instead of writing this out 12 times, why not do this? Why not see what it is squared and then raise that to the 6th power, right? Because now what that's going to allow me to do is when I find out that this 2 plus 5i squared is this number here, I can raise that to the 6th, right? Well, isn't that then going to be negative 21 plus 20i squared raised to the 3rd power? So what this does, if we're able to recognize this relationship with our laws of exponents, it condenses the amount of FOILing that we have to do, right? Okay. If I don't recognize that, the amount of FOILing is very tedious, very monotonous, and set yourself up for a lot of mistakes. A lot more mistakes than what this process already sets us up for. But if I FOIL this, okay, so negative 21 squared ends up being 441. Okay. We will then subtract from the, so we're going to multiply these two things together, and that gives me 420, and I'll double that, so it gives me 840, right? Okay, so I get, and it's going to be negative, so negative 840i. Okay, and now I'll square that. That gives me 400i squared, right? Well, plus 400i squared ends up actually being minus 400, correct? Okay, so this turns into 441 minus 840i. Is everybody okay with that? 41 minus 840i. Now, that was this innermost thing squared, right? We still have that power of 3 up there. Well, can't I then rewrite that as 41 minus 840i squared times 41 minus 840i? Okay, so this is where it starts to get really tedious, because these products then become very large, right? So let's see. Let me try to move some stuff up here to save some room. Which is a better way to grab all this stuff. So let me put this stuff here. And then that there. Okay. So now I'm going to multiply this out. I'm going to square that. I'll write it right here. So 41 squared gives me 1681. Okay. I will now multiply these two numbers together and double it. So 41 times 840. And then double that. So it becomes negative 68880. And now I will square this last thing. So it'll be a negative times a negative, so that turns into a positive, right? And then I'll have an I squared, so it turns it back into a negative, correct? So I'm looking at a negative here, and then whatever 840 times 840 is. And here's where you start getting very large numbers. They get kind of messy. That's got an I on it. So 705600. So 1681 minus 705600 ends up giving me this number here, negative 703919 minus then 68880i. That is 41 minus 840i squared, right? I now need to multiply that by this, because that will be the, ends up being really like the last foiling. I've now got, you know, basically inside those parentheses, I have what? That would be z to the 11th, right? Actually, no, that wouldn't be. It'd be z to the 8 minus 40i would be to the 4th. Is that right? Let me just double check real quick. So 2 plus 5. I should have kept track of this as we went through. Squared. 4. Okay, so the 41 minus 840i, that is 2 plus 5i to the 4th. Does that make sense? The 703919 number minus 68880i, that would be then 2 plus 5i to the 8th. Does that make sense? Okay, so taking the 8th power times the 4th power, obviously, then that's the 12th power. So when I FOIL this, I will take that number times that number. Okay, so that's going to be ugly. Times 41. So it gives me negative 2,886, 0,679. Okay, it's first times first. Let's go outside times outside. So negative 703,919 times 840, negative 840i. So it's going to give me 591291960i. Now I'm going to do inside times inside. So the 68880i times 41. And it's going to give me negative 2824080i. Now we'll do last times last. So last times last will give me, I'm just going to kind of take care of the I squared all at once here. A negative times a negative would make this positive, right? But then the I squared is going to make it negative. So I'm going to take 68880 times 840. And it gives me 57,859,200. So, combine like terms then. That first number, negative 2,886,0679, minus this number out here, gives me negative 8,671,9,879. And then when I add these two I components together, we've got negative, yes. Is that positive? Yes. Because this was a negative times a negative, right? Good call, thank you. So we got that positive. And then minus the 2824080. All right, so it gives me plus then 5,884,678,880i. That's our answer. Okay, that is 2 plus 5i raised to the 12th power. Okay, so it's very small numbers doing fun, right? Raised to the 12th power, that formulating process just amplifies those numbers so fast. Okay? So that being said, on a test or quiz, are they going to ask you to go to 12th power? Probably not. Maybe the 4th power, 5th power. But I want to do one big enough to see that that's time consuming, right? And hopefully you see all the different places that we can make a mistake. All right. Let's so I've got that number already written on the whiteboard up there, right? Let's do this through de Moivre's theorem and see if there's any change in the speed in which we can do this. So de Moivre's theorem, remember, said z had to be in polar form. So if z has to be in polar form, I have to find r. And if you remember, r is just a squared plus b squared. Now, remember, the a is the 2, the b is the 5, right? The I does not get placed into the r formula, okay? The I part is more of an identifier to tell you that that's the imaginary component, but you don't do anything here with the I in regards to the radius. Okay, so when we find that, it's going to be the square root of 4 plus 25, right? So root 29, there's your R value. Theta now, remember, theta is always found by tangent inverse of B over A. All right, now with this one, B and A are both positive, so that means this is in the first quadrant, right? So the theta that my calculator spits back here, if we go, just grab this in Desmos real quick, arctangent of 5 over 2, 68.198. So B was 5, A was 2. So 68.19. All right. Now I'm going to, right now, just for the sake of writing these down, I'm going to just kind of round to a couple decimal places here. But when we then see our final answer, I'm going to grab Desmos and try to develop a procedure in Desmos so there's no rounding. Okay. So that is Z with its polar properties. So we would write Z in polar form as R. Cis then theta, 68.19. Okay. What I would do, guys, just before, we're going to go on to doing more work, and this is something to think about. I think it's important to kind of periodically check whether what you're doing is accurate. So I want to see, is square root of 29 cosine of 68.19, is that pretty close to 2 plus 5i? Now, obviously, that's close to 2, right? Now, this junk here is because I rounded that 0.19 pretty egregiously, okay? If I replace these cosine with sine, then it should give me a number pretty close to 5. So I know that's a pretty accurate description of Z in polar form, right? Okay. I think that's a great skill to develop, is to check where you're at and what you're doing periodically throughout the problem. Because then when you're done and you get the right answer, it's right because everything on the way to that was right, correct? Or when you get done, you get the wrong answer, but you know everything up to the kind of the last step was working out. You know where to pinpoint your error. Does that make sense? It's kind of like when you're putting a car together. When Ford puts a car together, they don't just throw everything together and then go turn it on when it's done, right? They check periodically through the line whether those systems that they're working on are working. Because then when they get that finalized car at the end, it's going to work the way it was intended to. Okay? Okay. So now, if that's Z, then Z to the 12th would look this way. Remember, De Moivre says Z to the nth is equal to R to the nth cis in theta. So we're going to go root 29 to the 12th cis 68.19 times 12. I'm going to kind of condense this a little bit, make it cleaner looking. Okay. This 29, root 29 to the 12th, is that the same thing as 29 to the 1/2 raised to the 12th? What's a better way of writing that? 29 to the 6th. So it just gets rid of the radical. You don't have to do that. You're going to get your calculator out here in a moment anyways. Okay, so now when I take the 68.19 number, let's do this in Desmos real quick. So 68.19 number came from the arctangent of 5/2. And here's the issue where, there we go. Here's the issue where if I round that to 0.19, and then I multiply that by 12, because that's what that argument needs to be, right? If I were rounding that to 0.19, then I've now amplified that rounding error 12 times, right? That could be a big deal. So try not to do that. Now that number right there, you can use that. So I can write this as 8 down here, 818.383. Okay. But what did we say yesterday? We like that number to be between what two values? Yeah, 0 and 360. So I'm going to write this way. We'll take that number and subtract 360 one time. And that doesn't get between 0 and 360, right? So subtract it a second time, and then we get 98.383. 98.383. Now, somebody in the last class said, if you wanted that as your answer, because that is Z to the 12th in polar form, would it be okay if we wrote it as 98.383? I'd be fine with that. Now, obviously, if we go through and we multiply this out, we're not going to get that 86719,879 number. We'll get something like close to it, but we're not going to get to that exactly. Okay. So what we're going to do here is I'm going to go 29. So this number here, this is the nice thing about Desmos, is I can define variables. I can say A equals that. So the next time I hit A, I get that, right? Does that make sense? So now what I'm going to do is I'm going to go 29 to the 6th times cosine of that A. Does that give me that number that we have up there on the board? Okay. Now the complex part would be when that cosine changes to a sine. Is that the number that we have up there for the complex part? Or the, I guess, the imaginary part. Was that quicker? Right? And my argument, even if it wasn't quicker, there's a lot less places to make mistakes, I think. There's a lot less multiplication and adding and subtracting, that kind of stuff, to where you can make just those arithmetic errors. Okay? Questions on that? I want you guys to do one more, but I want you guys to get a start on it. Let's go -3 plus I, and let's raise that to the 10th power. Okay? So don't do that using rectangular form. Go ahead and just get going with that in de Moivre's theorem. When you guys do tangent inverse, okay, of B array, so it's tangent inverse of 1/3, right? Or tangent of 1/3. Okay, so I get that. Now, we are in the second quadrant, so you might have done this. And that's fine. It just changes because the relationship we know about our even and odd function just changes the plus or minus of that 18 degrees. Does it matter, though? Is that even the theta that I'm interested in? No. Okay. So the way I think about it, guys, if I'm working with tangent in the second, third, or fourth quadrant, I do not care whether I put plus or minuses on the b's and a's or the x and y's earlier with the other ideas that we're working with, because I know that my calculator is only going to give me things back between -90 and +90 anyways. So that's probably usually not the angle that I'm even interested in. Okay. The angle that we're going to be interested in is what in comparison to that 18. What do I need to do with that 18 degrees? I need to do that, don't I? Okay. Because if I go -3 plus I, so there's -3, let's say that's I, so now I'm talking about that triangle. So the 18 degrees that I was getting is that angle right there, right? If it was -18, it'd be talking about that angle right there. There's a relationship, they're vertical, correct? But what I'm really interested in, because this is in the second quadrant, what I'm really interested in is that theta right there. So that's taking the 180 minus this 18 to get the 161. Okay, so that's one little intricacy with some of these questions, depending on what quadrant you're in. Theta is not necessarily directly only what you get out of this. You might have to adjust it a little bit. Okay, you might have to add it to 180, subtract it from 180, or subtract it from 360, depending on what quadrant you're in. Okay, so we get that. So theta, 161 0.565. Come on. All right. So then z to the 10th. Remember what de Moivre says. Z to the nth is r to the nth cis n theta, right? So here's our z. So we're going to go root 10 to the 10th cis 161.565 times 10. It's kind of nice because this turns into 10 to the 5th, doesn't it? 1/2, right? 10 to the 1/2 raised to the 10th. 10 to the 5th. This is, now if I got times 10, I just move the decimal place one spot to the right, all right? So 161.565. There's my theta. Okay. Now, 10 to the 5th, 100,000, right? Okay. So let's kind of look at this stuff here real quick. Clean this up. We've got, I'm just going to find out, so we went arctangent of 1/3. We removed that from 180. Gave us that number there, right? We then took that and multiplied it by 10. So now that number is my argument. But I don't like that because it's between, or it's greater than 360, right? So I want to start reducing it by multiples of 360. So I could do that. If you're working on your TI 384, if you hit minus 360 and hit enter, and hit minus 360 one more time, and then hit enter, and then hit enter, and then hit enter, it will do that kind of repetitive removal 360, right? Okay. I like this because I can do the same thing here, but put maybe a 1 there. That didn't work. Put a 2, still not between 0 and 360. Make a 3, make a 4. There we go, right? Okay. So there's the theta that I'm really interested in. So I'm going to call that A. Okay. And then, obviously, 10 to the 5th. You see that is 100,000. Okay. And then we're going to go cosine of A. So there's that value. That's your A value, right? And then we'll go 10 to the 5th times sine of A. And there's my B value. So this thing turns into negative 99712 plus 7584. Okay. Now, all that being said, I get to the, let's say the final. Now the final, obviously at the top of the final says show all work or no credit, correct? And I'm usually pretty lenient with the work that we show, but if you just have this written down as the problem and you get just this as the answer, there's no work involved here. I'm not giving you credit for it. However, maybe this would be useful. You guys have the ability to go -3 plus. Now, I is second, and then your decimal. If I raise that to the 10th power, your calculator generates that for you, right? Okay. Now, if I go to certain powers here, just because of the capabilities of that calculator, it might eventually say like an overflow error, meaning that your numbers, your decimal places are too big for it to do the calculation. But if I was doing this problem, doesn't it make sense to know what the answer is before I go through and do the work? Okay, so it's kind of something maybe to kind of hopefully develop a proficiency for in other areas of mathematics and in science as well, your physics, your chemistry, and that kind of stuff. To know the answer, to have an idea of how to get the answer first using other means, and then walk myself through the process that I'm being graded on. Obviously, if we go through that process and we get to the answer, we know when the process was right. Is that cool? We do that kind of stuff? All right. Like I said, do we have great